All right. So I could have those exams back to you on Wednesday. I may post the grades tomorrow at some point. So you might see those pop up on Canvas, but I'll definitely go be posted before we start class on Wednesday, and I'll hand them back at the beginning of class. So from there, just some housekeeping stuff before we get into material today. I put up the next Connect assignment, so you can start working on it as we cover material. I mentioned this a lot. I think it's going to make it a lot easier over the next 4.5 weeks of the running the semester. Try to work on these homework kind of as soon as they get out there, kind of chip away at them, so you don't have to kind of wait until the due date. Other than that, I don't think there's anything else I want to say. I'll try to get those Excel graded fairly quickly this week as well. I should be able to do a good majority of that tomorrow. So hopefully those will be done before Wednesday, but I'm given my schedule, I'm not going to promise they'll be done before Wednesday, but definitely by the end of the week. Okay. Any other questions before we jump into material here today? Okay. So I put up the next kind of set of lecture slides right here. So we'll be starting with it. I'm actually going to jump around a little bit. I kind of changed my mind. I just wanted to make sure I had them in there. So I'm going to go on slide 13. We're going to start from there. Okay. So we've done some hypothesis testing for 3 different scenarios. We had a sample mean, and we didn't know the population variance. We had a sample mean, and we knew it. And then we also had proportions, right? Sample proportions. So that was all for one population, right? We're looking at one variable. So what we're going to do next is we want to be able to compare 2 different groups, right? So I'm going to have 2 populations I'm sampling from. Then based off those samples, I want to make statements like, well, does this group have a higher average salary than this other group, right? Or does this country have a higher proportion of people below the poverty line than this other country? Right? These are kind of questions we can start asking. Right? So we're going to still have the same kind of 3 setups, right? We're going to have a situation where we're taking samples from populations where we know the population variance. Looking at sample proportions, we're taking 2 samples, but we only have sample variances. We can do the exact same thing for hypothesis test, and all the principles of what we were doing before, everything applies exactly the same. Okay? So nothing should really change in terms of the procedure. It's just when we do things like calculate the confidence interval or calculate our test statistics, that's going to look a little bit different. But looking up p-values, making the rejection decision, interpreting what that confidence interval is telling us, is really going to be very similar, almost exactly the same as what we were doing before. So I wanted to start out, and then we'll get to a match pairs. That probably won't be till next week, so we'll kind of punt on that. But it's a similar idea where we're comparing 2 groups. Okay? So just to give you some motivating examples, and then we'll do a little bit of confidence intervals, and then we'll do some more hypothesis testing today. So maybe I have this idea where I've got, Econ and theater majors. I have their starting salaries, and I know the population variances or population standard deviations somehow. And I want to make a 95% confidence in what that true difference is between econ, theater major, starting salaries. I might want to do something like I've got 2 time periods, right? So I have this old survey about the Affordable Health Care Act, and I want to compare 2010 to 2011 and say, did the proportion of people who found this favorable, right? So Affordable Health Care, did that proportion increase? Did it decrease? Did it stay the same? I might want to look at people who are texting versus not texting while driving. I look at their response times, and I want to say, what's the true difference in response time between when I'm texting while driving versus when I'm not? So these are all kind of the motivating examples, and we'll end up working through each one of these. But the first one that we're going to look at is when we have 2 population means, and we know the population variances. Okay? I'm going to build this first, try to relate to what we were doing before. So when we were looking at a 1 population example, when we had a sample mean, and we knew the population variance, this was going to be kind of our setup, right? And it was really similar across all these different types. We're going to start out with our sample statistic. We're going to go a certain number of standard deviations to the left and the right. That's our z-value. And it's going to be the z that corresponds to having half of alpha on each side of our confidence interval. We're then going to multiply. Well, if that's the number of standard deviations the way we want to go, we then multiply that by what the standard deviation actually is. The standard deviation of that statistic we're looking at, which was the sample mean. And then we said, well, we know we find the standard deviation of our sample means. It's the original variance divided by the sample size. And then we want to take the square root to make it a standard deviation instead of a variance. We're going to do something very similar when we're looking at and actually draw this up here. We had one population. Kind of thought about it like this, right? And I'll write the variance just to make this a little bit easier when we first look at it. That was what we knew was true about the distribution of sample means. They should have a mean, or they should be centered around that true population mean. And the variance of our sample mean should be the original variance over our sample size. Well, the same thing is going to be true if we're looking at the difference between our sample means. As long as we get these sample sizes over 30, or the original data is normally distributed, we know something not about the distribution of our sample means, but the distribution about the difference in our two groups' sample means. Okay? And what will end up being true is they'll be normally distributed as long as we get those sample sizes over 30. And the mean of this difference in our sample mean. So this is the idea, like, let's do the econ and theater major starting salaries. I take a sample of econ majors, theater majors, calculate their sample mean starting salaries, take the difference, write that number down. I take another random sample of econ majors, theater majors, find the sample means, look at the difference, write that number down. I do that 1,000 different times. I could then look at, well, what's the distribution of the difference in those sample means look like? And what ends up being true is they're always going to be centered, around whatever that true difference is. So even though I can't observe the true population mean for econ and theater major starting salaries, my sample means, right, the difference in those sample means will be normally distributed about whatever that true difference is. We also know something about the variance of this new statistic we're interested in. So we're no longer interested in just the sample mean, but we're interested in the variance of the difference in our sample means. What ends up being true is the variance, when you're looking at the difference between two variables, it's just you add up the variance of each one of those things. So this would essentially be the variance of the first group plus the variance of the second group's sample means. Well, we have an equation to calculate the variance of a sample mean. So this ends up just becoming the variance of the first group over the sample size we took from that group, and then plus the variance of that second group divided by whatever sample size we took from that second group. And then if I wanted to make it a standard deviation, I just take the square root, same kind of idea, right? So it's going to follow the kind of a similar kind of pattern, right? Just now, instead of a sample mean, looking at the difference in sample means. So instead of being centered around the true mean, it's centered around the true difference in means. Instead of the variance in one sample mean, we're looking at the variance of the difference in sample means. Right? So we now have the variance of the statistic we're interested in. We have the mean of the statistic we're interested in. We could take certain values, turn them into z-scores, look up the probability to the left or the right. So if we break this down, right, this would be kind of something we want to start using, right? The mean of that difference in sample means, whatever that true difference is. And then our standard deviation, well, that was just the square root of the variance. And the variance of the difference in sample means, so the variance of each sample mean added together. So hopefully now, if we think about what we were doing with our old confidence interval, we can build confidence intervals for what that true difference is between econ and theater major starting salaries. What are we going to base that around? You had to guess. If when we were looking at one group, we based our confidence interval around the sample mean, we're looking at the difference in sample means, we're going to base our confidence interval around, well, what's the sample statistic that we're actually observing? Taking a sample from each group, we're then going to look at what that difference is. So if I go back to my econ theater major starting salaries, I found one had 45,000, the other was 33,000. So my sample evidence, that sample difference I found, the difference between those two sample means would be what? 12,000. That's what I'd be basing my confidence interval around. Or I'm going to be basing it around whatever sample statistic I found. The statistic I'm now interested in is just the difference in sample means. So I base it around that difference in the sample means. What's nice about two populations, the next part of this is exactly what we were doing before. We then want to go a certain number of standard deviations to the left and to the right, and we can use that standard normal distribution since we know our population variances, right? We don't have this dividing by n-1 problem, right? So we look that value up the exact same way as what we were doing with one population. We then are going to multiply by Well, if this is the number of standard deviations where we want to go, we multiply that by the standard deviation of the statistic we're interested in. Well, what statistic are we interested in? The difference in sample means. Well, we have an equation for that, right? Got it up here on the board. So this is just going to be the square root of each group's variance divided by that group's sample size. So the confidence interval equation has kind of like twice as many moving parts, but really when you break it down, like here is what your sample mean was before, and you're still multiplying by a standard deviation. It's just to calculate the standard deviation of this new statistic you're interested in. It's got a couple more moving parts. Okay. Other than that, like the principles of what we're doing kind of apply exactly the same. And like I said, looking at that z-value, that's exactly what you're doing it for. So work through an example here. We put this all together. I kind of already outlined this on the board. All right, we can kind of compare this to what we're doing with one population. Okay. So here's our generalized steps. If you ever, oops, there we go. It's now we've just got twice as many things to identify. So instead of one sample mean, one population variance, we've got two sample means, two sample variances. Then we've got two sample sizes now. We still are going to be concerned with what level of confidence. So we look at what alpha is going to be. Use alpha to look up this z-value that gives us half of alpha on each side of our confidence interval. And then our upper and lower bound equations, it's a little bit more complicated. All right, we've got kind of a few more moving parts now. So if I think about, oh, come on, my motivating example, right? Let's say I took this sample from econ majors, theater majors. I know the population variances, and I want to build a 95% confidence interval for what that true difference in salaries is, will be. So I'm going to get rid of this since we're not doing this. I'll leave the confidence interval equation up there so we can just kind of follow along. So the initial part of this confidence interval is I'm going to have this formula on the formula sheet in front of me, or I could have this formula as I'm working on the homeworks. I'm just going to start plugging in what I know. So I'm going to define the difference between econ and theater majors. So here, think about group 1 is my econ majors. Group 2 is my theater majors. I'll kind of mention why this doesn't really matter, but for the sake of starting out, econ majors are group 1. Well, what was the sample mean starting salary we found for econ majors? 45,000. Right. What was the sample mean starting salary for theater majors? 33. So whatever that difference is, that's what I'm going to base my confidence interval around. That's the best guess I have about what the true difference is in these salaries. So, if it makes it easier, I could just write this, right, as one number, right? Just so when I go to my calculator, I don't have more parentheses and things going on. We'll look up the z-value in a second, but plugging in the additional things I know, well, I need to take the square root of each group's population variance. So the first group's was 9,000. The second group's was 6,000. And my two sample sizes were 40 econ majors, 50 theater majors. So notice here, we don't have to have the same sample size from each group. A lot of the times we will, just to kind of keep it balanced, but it's not always the case, right? Depending on who we could kind of get to be part of our survey or respond to our survey. So I've really just plugged in the information I was given up to this point, right? Now in practice, I might have some actual data and I calculate the sample mean, in Excel, I can use the average function. I look at the sample size using the count function. I was given the known population variances. The only thing left I need to do is look up this z-score. That's going to give me half of alpha on each side of my interval, right? Or alpha total, if I combine the sides. So at the 95% level, hopefully this one, what should my alpha value be? Yeah, 0.05, right? It's the same thing as what we were doing before. 90%, 10% outside, decimal form, 0.1. 95%, 5% outside, 0.05. 99%, 1% outside, 0.01. So I've got half of alpha on each side. This is what, 0.025. The next step, I'm going to go to my z tables. I know the area that I want in each tail is 0.025. So I go to the middle and I start to look for that value, or at least what's closest to it. So I keep scrolling down. Looks like it's right here. So that would correspond to negative 1.9 6 is the z-value that gives me that area of 0.025 in the tail. But remember, when I look these up, I'm finding the z-value, and if it's negative, well, that's how many standard deviations below I'm going to get my lower bound. I would go that same number of standard deviations above to get my upper bound. Right? But that was the last thing I needed. Now it's better getting this entered into my calculator. Once again, if I'm working through these, I break this down into a step, calculate this first, just so that this is one value I can plug in. I then might do the simple math here, right? So then I just have that one value of 12,000 to use. And then once I do that, it looks just like what we were doing before. Any questions about how I found that z value? Yeah.
The last part of that problem.
Mm-hmm.
So you don't square the population variance. Like on the equation it says to square it, but you don't
Square this guy?
Yeah.
Let me see. Like in the slides, it says that.
I don't know. I usually when I see that equation.
Yeah. So let me go back to this equation now. I think I know what you're asking. So these are squared, right? Remember, what represents the variance? Sigma squared. So when I'm given the variance, that is the variance. So I just have one value. If I just gave you the standard deviation, like some of the practice exam problems we had, if I just have the standard deviation, then yes, I still need to square it. Any other questions on that?
The standard, it's the difference between the standard deviation and the standard variance.
So my standard deviation is this, my variance is this, right?
Yeah.
Yep. So if I know the standard deviation, I can plug that in and then square it to get the variance. There are questions on that before we keep moving. So if I go plug out all my, I kind of get it written up here on the board. These are all my steps. I can go through and calculate that upper and lower bound. Okay. So here, I think I chose variances that were far too small for salaries, but it still helps to make the point of, I now could say with 95% confidence, based off the sample evidence I found, the true difference in starting salaries between these two majors is between what, 11,900 and just over 12,000, right? This is a pretty narrow range of values. I think in reality, if I look at actual income data, these variances are going to be much higher. But for the sake of this example, all we want to know is this interval tells us with 95% confidence, the true difference between these major starting salaries is somewhere in this range. Okay. Questions on that before you kind of keep moving? I'm going to introduce something else with hypothesis testing. I just want to kind of dip our toe into this, looking at these examples where we've got the difference in sample means, but we know the population variances. Well, we can build confidence intervals, but we can also do hypothesis testing. Oops. So I'm going to skip ahead here. So I've got another example, just different values, right? So it would be the exact same thing. I guess we could work through this one. Let's say I'm looking at what? Indiana and Ohio. I want to compare their robbery rates, right? I want a 95% confidence interval for the difference between Indiana and Ohio. Well, once again, if I've got my general form of the equation, Indiana is my group 1 here. Ohio is group 2. So I'm going to base my confidence interval around whatever the sample difference I found was. Well, for the first group, I found a sample mean of what? 109. Second group I found was 163 crimes per whatever 100,000 people. So that true difference I found, what, negative 54. So that's what I'm basing my confidence interval around, right? That true difference in those sample means. So if I'm looking at the answers up here, which of these doesn't really make any sense? I mean, one of these things is not like the other. Yeah, D, right? What has to be true about my confidence interval? I am basing it around that sample difference I found. The sample difference I found was negative 54. That should be smack dab in the middle of my confidence interval. It's not even in this. I think the other ones it is in the middle, so you can't rule any of those out. But D doesn't make any sense at all because we found a sample difference that was negative, and that should be exactly in the middle of our confidence interval. Okay. From here, just a matter of, okay, well, what was the variance of group 1? I think I was told it's what? 175. And I had 24 years of data, so that was my sample size. The second group had a much higher variance, 497. And I had 24 years of data from that state as well, so my sample size being 24. The only thing left that I have to do is figure out what this Z value is. And I erased it, but before, what was our alpha value?
1.96.
Yeah, so we had 95% confidence interval corresponded to an alpha of 0.05, which meant we were looking for the Z value that gave us alpha total in the tails, or half of alpha in each tail, 0.05 over 2, 0.025. We went to the table. If we look up 0.025 again, we're going to find that exact same Z value of 1.96. Okay. So when we're dealing with a standard normal distribution, we're going to see for these 90, 95, 99% confidence intervals, it's the same three Z values. It's what, 2.58, 1.96, and 1.65-ish, right? It's always going to be those same values, right? So if we keep that confidence interval the same as we had in the previous example, we can, can't really skip that step, but we know what that value is going to be, right? We already found that Z value. Okay? Any questions? So we identified everything, plugged it in, right? Any questions along the steps here? Like, yeah.
But when plugging it in, you just plug it in all like as it's written on that, and then you get the same result, because I've tried it.
When you're talking about like getting it entered into a calculator?
Yeah.
Yeah, so this is where give you a couple tricks or a couple tips for like using your calculator. Like I said, I would always calculate this first so that it's one number. And in calculating that, I need to make sure I don't have the square root of 175 and then hit enter, because that would just be taking the square root of 175, then dividing it by 4, and then, so I need to make sure that I have this entire value and then take the square root. So one thing that can help is if you work backwards, it actually solves your order of operations kind of problems for this. So if I take 197, divide that by 24, then add to that 175 over 24, then I have that value. Now take the square root. I can't mess up that order of operations as easily. So sometimes I tell people, like, working backwards, as weird as it is, right? It can kind of prevent if you're not using the parentheses correctly and things like that. But in general, yeah, calculating this just so that it's one number makes it a lot easier to make sure you're not going to make an error in your calculator there. Similar kind of thing over here, right? If I forget parentheses or whatever, just find this value first. Now I just got one value to put in. Any other questions on this one before we keep going here? So it's a little bit of interpretation of these confidence intervals now. So if I'm looking at my upper and lower bound, it's -64 to -43. With 95% confidence, what statement could I make here? If I'm looking at robbery rate differences between Indiana and Ohio, with 95% confidence, I could say what is true about Indiana relative to Ohio.
Less likely that there's crime, or crime is not occurring.
Not even less likely, but with 95% confidence, the only values for that true difference in crime are negative, which would imply, what's the only way that this difference is negative? If Ohio's robbery rates or crime rates are greater than Indiana's, right? So here with 95% confidence, I could say Ohio has a bigger problem with crime than Indiana. Now, if they were only positive values, would flip that, right? I would be saying, well, Indiana has higher crime rates with 95% confidence. Okay? So this is how we can start to use these confidence intervals to compare between two groups. And, here saying, one state has a bigger issue with crime or robbery. I forget now, I'm saying crime. Was it robbery rates? Yeah, so one state has a bigger problem with robbery than the other, okay? So we're then going to take this, instead of confidence intervals, we'll go right back to hypothesis testing, okay? So I'm going to introduce hypothesis testing for this type of a problem. I'm going to also introduce a new concept at some point called critical values, okay? So let's start out. I'll leave this confidence interval equation up here so we can kind of think about how we could do some hypothesis testing for the difference in sample means. So if we call the difference in sample means kind of capital D, like that's the true difference between the population means. So kind of think about it here. If I just define that true difference as the true difference between my two groups' sample means. Well, before, remember we were doing things like, was the mean less than some assumed true value? Was it greater than some assumed true value? Or was it not equal to some assumed true value? We're going to do the exact same thing with the difference in sample means. It's just now our alternative hypothesis will be, is that true difference greater than 0? Is that true difference less than 0? And is that true difference not equal to 0? Okay. So it's the same thing. It's just now we're not concerned with one sample mean, we're concerned with a difference. Now, you don't have to use this assumed true difference of 0. For the sake of this class, we always, or that's all I expect of you, right? I'll show you a couple examples, probably, I don't even know about this week, but next week for sure, where I just give you a taste of, you don't have to use 0 here. It's just 90+% of the time, that's usually the assumed true difference. And we can kind of think about why that makes sense. So I'll put this up here for a second, right? We've got the same type of test as before. We've got, look at the alternative hypothesis, greater than sign, right tail, less than sign, left tail, not equal to sign, two tail. Everything looks the exact same when it comes to finding p-values for these different types of tests. So we typically use this assumed true difference of 0 because we can imagine what that is really looking like. So I'll start out with something a little different. Let's say I go back to my econ theater major starting salary exam. And I say, what I want to test for is, do my econ majors have a higher mean starting salary than my theater majors? That's what I want to test for. But when we write out our alternative hypothesis, the statistic we're looking at is the difference. So even though this is what I want to test for, I need to somehow say that in a slightly different way. So instead of saying, do my econ majors make more than my theater majors? That is what I want to test for. That's my alternative hypothesis. The way I need to write it, well, notice if I just subtract this from both sides, what I then end up with is that true difference between the two groups greater than 0? Right? So a lot of the times the way we speak in English is going to look a little bit different than our final hypothesis test, right? If I'm interested in our econ majors have a higher starting salary than theater majors, really what I'm saying is, will the difference between the two be a positive value, right? Will the econ majors have a higher starting salary than the theater majors? And if that's true, then it would have to be a positive number, right? Greater than 0. So identifying the null alternative probably gets a little bit trickier with these two population examples. But other than that, same type of tests, look at the p-values the exact same way. Okay? So here's our kind of general steps. I'm now going to we're going to work through some examples where we look at this, but we're also going to do something that isn't the p-value approach. We're going to call the critical value approach. It's kind of like looking at the different side of the same coin, and I'll hopefully by the end of class, we'll kind of have somewhat of a understanding as to why they're very closely related. And no matter if I use my p-value or a critical value approach, I'll always make the same rejection decision. Okay? So before we get there, we kind of have these p-values. I basically just copy and pasted the slide that we had before. Nothing changes, right? For a right tail test, p-value is the area to the right of your test statistic. Left tail test, area to the left. Two tail test, the area in one tail, then multiplied by 2. All the same principles apply as what we were using before. So the critical value is going to work a little bit different. Before we get there, I just want to look at, well, what's the test statistic going to look like for these two population examples? So for our two population examples, instead of having our sample mean, so just to give you a comparison here, what we were doing before looks something like this, right? Where the denominator represented that standard deviation of my sample means. My new test statistic is going to be for the difference in my two groups' sample means. So instead of basing it around a sample mean, we're going to be basing it around, just like the confidence interval, whatever the sample difference we found was. We're then going to subtract the mean of this statistic. Well, we would usually subtract the mean. We don't know what that true mean difference is. All we have is this assumed true value. But like I said, I'm going to keep this like as 0 for you guys. So this actually makes the numerator a little bit easier, because subtracting 0 never changes anything. If I'm using that assumed true difference of 0, essentially I can ignore that. Right? So it becomes a little bit easier, kind of takes away one of the moving parts in our test statistic equation. We then divide by, it's the same sort of setup. We take our sample statistic or our sample difference, subtract the assumed true difference, that's 0, it's kind of easy, and then divide by the standard deviation of that statistic, or the standard deviation of that sample difference. Well, with confidence intervals, we said that standard deviation for our sample difference was the square root of each group's population variance over that group's sample size. So same kind of setup, right? I take the statistic I'm looking at, subtract the assumed true value of the population statistic, divide by the standard deviation of the statistic I'm interested in. Same setup here, it's just the statistic I'm interested in has changed from one sample mean to the difference in sample means. Okay. So we've got our test statistic. If we go back to the p-value approach, we could then use that, plot it, use it to find the p-value. But I'm going to go way back to the beginning of the slides for this week. In fact, instead of giving everybody a Caesar, I should probably just do this. Let me see. How high up do we need to go? There we go. So instead of looking at p-values, we're going to calculate that test statistic. And then instead of using that test statistic to find a p-value to then compare to alpha, what we're going to do is we're going to use alpha to find this cutoff value or this critical value for anything past this many standard deviations away from the assumed true mean, or now the assumed true difference. Anything that's past this point, I'm okay rejecting what I assume to be true, or I'm okay rejecting the null, right? So for these different types of tests, our critical values and our rejection regions will look a little bit different. I think a lot of times the critical value approach can be easier for people because there's a really nice visual that goes along with it. Okay. So what we're going to do is use our alpha to figure out what this critical value is. I'll then talk about how we identify our rejection regions. And if my test statistic falls in that rejection region, I can reject the null. If it doesn't, I fail to reject. Okay. So here, this is kind of the mathematical side of it. Let me get a nice picture and I'll come back to this because that's probably more difficult to look at the true mathematical way to write it. I think there's an easier way to understand. So let's say I have this example and I've got let me make sure I did a right tail test here. Yeah, I'll draw this up on the board. So let's say I've got a right tail test. So I know that my alternative hypothesis, if I'm using this difference, right, is that I'm wanting to test for, is that difference greater than 0? So I assume the opposite is true. So only evidence on the right side of this assumed true difference of 0 could go against the null. So what I'm thinking about is, okay, look, usually what I would do is look at that distribution of my sample statistic. I found some sample difference here. I don't know, let's call this, I don't know, we could use the ECON theater major starting difference that we found, which is $12,000. I then I know my population variances, so I can convert this into my Z statistic or my test statistic, right, using this equation. Once I have this Z statistic, right, I might want to do something like find the p-value. But instead of the p-value approach, we're going to use the critical value approach. We still need to do this step. We still need to turn that sample difference into our test statistic. It's just now what we're going to do is say, okay, look, I know that there is some critical value, which is still a Z value. It's just going to be like a cutoff Z value. And we're going to say there is some Z value that would give me a total of alpha in that right tail for my right tail test. What is that Z value going to be that gives me that alpha of 0.05 in the tail? Okay. So I go to my Z table. I try to find 0.05. Looks like I'm in between these two values. So negative 1 point. I can keep going up. 1.4, negative 1.5. So negative 1.5. However, why is that not going to be the critical value that gives me 0.05 in the upper right tail? When I looked up 0.05 in this table, the way the Z table works is that's actually the area in that left tail. Well, if there's 0.05 to the left of negative 1.65, that would mean that there's 0.05 to the right of positive 1.65. So for a right tail test, our critical values will always be on the right side of the distribution. In order for us to reject this null, we have to find evidence on the right side of the distribution. but it has to be far enough on the right side, right? Far enough away from this assumed true difference of 0 that we're okay rejecting at that level of confidence. So we'll use alpha to figure out what that Z value is that gives me alpha in the desired tail. For a right tail test, alpha in my right tail. For a left tail test, alpha in my left tail. And we'll talk about two tails in a second because that's a little bit different. But once I have that critical value for my right tail test, what that's really telling me is, look, if I find sample evidence that's more than 1.65 standard deviations away from what I assume to be true, well, that's far enough away that what I assumed is probably wrong, right? So I drew this test statistic first. Usually in practice, you'll want to plot your critical value, draw your rejection region, and then say, okay, look, where does my test statistic fall in relationship to that critical value? If, for example, my test statistic here was, I don't know, 2.2, I can reject at the 5% significance or 95% confidence level. If my test statistics somehow would end up being, I don't know, 1.1, well, that's not enough standard deviations away where I'm okay rejecting with 95% confidence, right? So this is why the critical value, it's a nice visual. Once I get that critical value plotted, and then I like plot my test statistic relative to that, if it's in my rejection region, I reject. If it's not, I fail to reject, right? So don't have to remember that it's p-value is less than alpha, or was it greater than alpha? No, here you kind of get this nice visual where as long as it's in that rejection region, you know you reject. Any questions on this before we keep moving on? I'm going to show you kind of what this looks like for left and two-tailed tests as well. So it's going to be a very similar thing if instead I had a left tail test. So we'll do that one first because I think that's a little bit easier. So let's say I wanted to find, I don't know what the example would be, the robbery rates one, right? Do I think that the robbery rates in the 8 are lower? So I want to know, is that true difference less than 0? So I've got a left tail test. To find my critical value there, I'm still looking up the Z value that would give me alpha in the tail that I'm looking at. Well, now I'm no longer looking at the right tail, I'm looking at the left tail. So let's say I wanted to find the critical value that would correspond to having 0.05 in that lower left tail. Well, I would look it up the exact same way I did before, right? I go find where's 0.05. So scroll down here, in between the same two values. Remember that was just negative 1.64 and negative 1.65. So now, with a left tail test, that is going to be the value I need, right? Because for a left tail test, only evidence that's a certain number of standard deviations below the assumed true mean or the assumed true difference, only evidence on the left side can go against the null. So here's my kind of cutoff value or my cutoff Z value. For a left tail test, my rejection region will be the area to the left. Okay? So similar kind of way we treat these one-tailed tests. It's just we always know the critical values for a right tail test are positive. Critical values for a left tail test are negative. Now, if we're looking at the same alpha, they're going to be the same value. It's just the right tail test, the critical value is positive. Left tail test, the critical value is negative. Okay? So before we move to two-tailed tests, I want to try to give some connection as to why these critical value approaches will lead to the same rejection decision as our p-value approach. So kind of erase this before I just make sure everyone, okay. I'm just going to draw it again so I can make this a little bit clearer, kind of clean this up a little bit, and then we'll take a look at two-tailed tests. But I want to really try to make this connection between our p-value and critical value approach. Okay? So let's say I'm looking at this sample difference. I don't know, I find that the sample difference is, we can just keep using that 12,000 value. I'll use the right tail test once again. So we can think about, if I was doing a right tail test and wanted to find the p-value, it would be the area to the right of that sample evidence I found. Right? So here, this would represent my p-value. Well, how do I find that? I need to turn that sample evidence into a test statistic. In this case, a Z statistic comes from a standard normal distribution. I could then use my Z table to find what's that area to the right. So another way I'll kind of write this, you can almost think about it as every test statistic has some corresponding p-value, right? Or some corresponding area to the right here. Okay? If I think about what I'm doing with my critical value approach, I'm choosing, well, not choosing, sorry. I am wanting a certain amount of alpha in my right tail, and I want to find the critical value that corresponds to having that amount of alpha or that probability in my right tail. So notice here, whenever my test statistic is to the right of my critical value for a right-tailed test, what's in my rejection region? I should be rejected. But notice, if my test statistic gets smaller, what's going to happen to my p-value? So remember, the p-value is that area to the right of my test statistic. So if my test statistic starts to get smaller, my p-value is going to get bigger. Yeah, I've got a much larger area. But notice when my p-value is getting larger, well, now my p-value, that area, is no longer less than alpha. It's now greater than alpha, so I stop rejecting, right? Fail to reject now. Also, once that test statistic gets smaller, well, now it's not in my rejection region, right? So it's almost like, you know, if I were to give you like a set of numbers where every number was twice itself, maybe this will help. So like 1, 2, 4, right? I could compare, this is X, this is Y. I know that if X is ever greater than 1, well, my Y variable would also be greater than kind of that Y variable, right? And so it's the similar idea here where you can either compare the values on the X-axis, right? I can compare my critical value to my test statistic, or I could think about if I plotted these areas in the right tail as my Y variable. Well, instead of comparing the X-axis, I could compare the Y variable of area in the tail, or p-value relative to my alpha. So that's why it doesn't matter if we use our p-value approach or our critical value approach, it will always lead to the same decisions. Because my critical values have a corresponding area in the tail. My test statistics also have a corresponding area in the tail. So we either can compare those areas in the tail, p-value to alpha, or we can compare the actual z values themselves, that z statistic, my test statistic, to my critical value. That's starting to make at least a little sense. Like I said, I'm not going to have it ironed out completely today, but hopefully you can kind of see like why these are both going to lead to the same decision, right? We're just either comparing the x-axis values, or you can think about the areas in the tail as like our y-axis values. So this is our right tail test. We took a look at the left tail test. The only other one I want to introduce today is how would we do this for a two-tail test? How would I find my critical values? So it's going to look a little bit different than a one-tail test. In fact, it's going to look very similar to something we've already done, which is it's going to look pretty simple, pretty similar to confidence intervals. So let's say I have a two-tail test where I want to know, is this true difference not equal to 0? I assume the opposite is true, which that it's exactly equal to 0. Well, now to find my z value or my critical value, that's going to be this cutoff, right? I'm thinking about now, oh, for a two-tail test, evidence on either side of my distribution could go against that null. So now what I want to find is there's some pair of critical values. Now they're the same value, but one's positive, one is negative, right? That's going to give me a total of alpha in my tails, right? So I want to find this critical value that gives me alpha total in the tails, which would mean that there is half of alpha in each tail. Well, now this looks very similar to confidence intervals, right? I've got half of alpha in each tail. So notice if we kind of do that 0.05 at 95% level, now we're down to 0.025 in each tail. We looked that value up earlier, but I could go to my z table, find 0.025, find that corresponding z value. We did that earlier, and that would be 1.906. So you still look up critical values the same way for a two-tailed test. It's just that you no longer look up the area of alpha because you don't have just one tail. You've got two tails now, so alpha total is in your tails, or half of alpha in each tail. So a two-tailed test, when you're looking up those critical values, identical to when you were looking up those z values for a confidence interval. So hopefully, we're taking a lot of things that we've kind of already seen a little bit of here and there, I've got kind of this new idea of critical values, but it's still using this idea of we're just using the inverse process. We know the area we want in the tail. We're trying to find that corresponding Z value that gives that to us. Okay. So I think in the slides here, I've got kind of this a little nice summary. I'll blow this up a little bit. And you can like write it out mathematically. Like I said, I think it just gets a little bit more confusing because negative values, I need something that's less than the positive value, right? So that kind of makes it a little bit more difficult. If I just think about the visual, my critical value for a left tail test, always going to be negative, and whatever gives me alpha in that left tail. Critical values for a right tail test, always positive, and they give me alpha total in that right tail. Two tail test, I have a pair of critical values, same number, one's positive, one's negative, and it's going to give me alpha total in the tails, so I'll have half of alpha in each tail. What that's going to mean, if I go back, let me see. Yeah, I think I skipped it. It was up here. I don't know why I put it in that order. When I'm looking up these critical values for a right tail test, I'm always going to find the same three critical values that are three different alphas. For a left tail test, it's going to be those exact same three values. Because it's a symmetric distribution, now I'm looking at the left side, those values are negative. And then for a two tail test, well, they're going to be a little bit greater because it's no longer alpha in one tail. I've only got half of alpha in the tail. So we'll start seeing these values pop up a lot, right? Because we're going to keep looking at the same three benchmark alphas. Okay. All right. So let me think if there's anything else. Kind of went over this. Like I said, this is like the mathematical slide. It gets a little bit confusing. But one thing you can do if for whatever reason the visuals don't connect with you. Really what we're doing anytime we had a left tail test, we wanted to know like, was our test statistic more extreme than our critical value? If we had a right tail test, we were saying, is that test statistic more extreme than my critical value? It's just that for a right tail test, it would have to be greater than. For a left tail test, it's actually less than, it's a larger negative value. So another easy kind of rejection decision is if the absolute value of my critical value is ever less than the absolute value of my test statistic or my Z statistic, well, then I can reject. If that doesn't hold, then I would fail to reject. Okay? So the absolute value kind of drops the negative signs, makes it nice and easy. Anytime I see sample evidence that is a higher number of standard deviations away than this cutoff number of standard deviations away, that correspond to my alpha value I wanted, then I'm okay rejecting. If that ever doesn't hold, I would fail to reject. So I think what we're going to do next class is I'll keep working through probably some hypothesis testing for the sample difference or the mean difference in sample means. We'll then kind of look at, we can do this exact same thing, but for the difference in two groups of sample means. Okay, we'll do some confidence intervals of that, some hypothesis testing. I should have those exams back Wednesday at the beginning of class. Other than that, before you guys get out of here, make sure everyone's just going to get 10 out of 10. Everyone's pretty attentive, asking good questions today. Just respond with any letter. Let's get credit for kind of being here today with a full 10 out of 10. Other than that, once you get that done, you can leave. I'll see you guys on Wednesday.
Then they go